Let's go.
Today we'll be teaching you Chapter 11, Understanding Randomness.
As we've learned, the definition of random has two parts. The first part is, every outcome is equally likely, and the second part, every subset of outcomes of size n has the same probability.
In this slideshow, we will be covering the importance of randomness, simulations, and what can go wrong.
Today, Mary and I will be talking about why be random. The most important thing to realize is that randomness equals fairness. Two main parts of randomness is nobody can guess the outcome before it happens, and when we want things to be fair, there are usually some underlying set of outcomes that will be equally likely. Now Mary will give you the definition of randomness again.
The definition is every outcome is equally likely, and each outcome has the same probability of occurring. So an example of randomness would be like rolling a dice. You don't know which number to land on, and each side has the same probability, which is 1/6.
So we're going to be talking about more reasons of why to be random. The reason you can be random, or should be random, is because it's more fair if you're going to, like, for example, choose a team. So one way of doing a random choosing would be to flip a coin. Would anyone like to flip our coin? Oh, Jake would.
So first call, heads or tails?
Do I get to flip it?
Yes.
Flip it.
Heads. Tails.
So you don't know the outcome of the match before you flip the coin, and so it's completely random because you cannot predict what the outcome will be.
Statisticians use randomness as a tool. It is fairly difficult to find a truly random piece of data.
Pick a number between 1 and 4. Raise your hand if you chose 1. Raise your hand if you chose 2. Raise your hand if you chose 3. Raise your hand if you chose 4. About 75% of all people choose 3. About 20% picked 2 or 4, and about only 5% pick 1.
Here's my random number generator, Jake.
92530300686.
Okay. So can humans truly be random? What was that? Why'd you pick those numbers?
That's my phone number.
Okay. So what can be random? Because obviously humans can't be random.
Well, if humans can't be random, then computers can be random.
Well, you see, computers aren't truly random. The sequence is not truly random in that it's completely determined by a previous algorithm, determined by already made up by a human previously.
So technically, there's not really anything that is really random.
Not really.
Except for this.
There are ways to generate random numbers so that they are both equally likely and truly random.
The best ways we know how to generate data that give a fair and accurate picture of the world relies on randomness. And we can draw conclusions from that randomness in certain areas which relate to sports and when they do coin tosses and how randomness can benefit one team or the other. So.
Today we'll be talking about simulation. A simulation is a collection of things that happen at random, and it's an action, not a tangible thing.
So Katie, flip this coin 500 times.
Wait, Savannah, that's the point of simulation. I don't need to flip it. I can put all the data in the computer and it will give me the random number.
Another part of simulation is a component. This is the most basic event. And a component, or the most basic event, also has its own possible outcomes. One of the outcomes will occur at random.
Okay, today we're talking about give me a T.
T.
Give me an R.
R.
Give me an I. Give me an A.
A.
Give me an L.
L.
Trial.
Sorry, Lizzie.
Okay, the sequence of events we want to investigate is called a trial. Trials usually involve several components. After the trial, we record what happened, our response variable.
Let's flip a coin.
Tails.
Flip another coin. Tails. Do it again. These are all response variables. Tails. Wow, 3 in a row. Maybe we can get a heads. Let's go, Abby. Heads. There we go. One head. Man, what a trial. Wow.
Using statistics is very risky. You cannot make a false statement without a true critic noticing. So, in this case, we're using random numbers. When we do a simulation, we're basically making a bunch of trials and see the results within computer. But we cannot be sure that our arithmetic in our computer is similar to the true world, to our true world results. So the first thing we cannot do is overstate our statement, overstate our case, because we cannot truly be sure which trial our trial is exactly the same to yours.
So for the outcome, change the accuracy, which means like you will get the number from the math way, and if you flip a quarter, you'll get 50% to the both side. But if you really flip the coin, you cannot get really the number as the math tell you. So also this makes the last wrong thing that you didn't run the enough trials. So when you run the enough trial, like go infinity for a quarter, so you will get the 50-50%, or the number most likely that number.
We will be summing up what we've learned in Chapter 11. First, we learned that randomness has two parts. Number 1, no one can guess the outcome before it happens. Number 2, when we want things to be fair, usually some underlying set of outcomes will be equally likely.
We know that statisticians use randomness as a tool.
We learned that sometimes random values are not easy to get.
It's surprisingly difficult to generate random values even when they're not equally likely.
But computers have become a popular way to generate random values.
The best way we know to generate data that gives a fair and accurate picture of the world rely on randomness. And the ways in which we draw conclusions from those data depend on the randomness too.
We learned about stimulations, components, and outcomes.
And we also learned about trials, response variables.
We learned about the 7 stimulation steps.
And we learned that we should always be sure to indicate that future results will not match our simulated results exactly.
Also, a simulation model can help us investigate the questions for which many outcomes are possible and when a mathematical answer is hard to calculate.
We base our simulation on random values.
And like all models, simulations can provide us with useful insights about the real world.